So the physical properties of ionic compounds can be explained if we consider the theory about how ionic compounds stay together. So an ionic bond is the electrostatic attraction between oppositely charged ions, and that leads to a non-directional bond where the oppositely charged ions surround one another. The classic example being sodium chloride, where you get sodium ions surrounded by six chloride ions and chloride ions surrounded by six sodium ions. Okay, so one of the common properties of ionic compounds, which I'll also refer to as salts, is that they are hard but brittle. So hard because the ionic bond is quite strong, meaning that the ions have fixed positions and it's rather difficult to make them move positions because they're so strongly attracted to their neighboring ions. So this is in or this is different than metallic bonds. Metallic bonds have positive ions in delocalized electrons, and the positive ions are able to move um, if you put a force on them because the delocalized electrons can maintain an attraction if the position of those positive ions moves. That's not the case with ionic compounds, however, because if you put a force on the ions, like this hammer is showing here, and you move the ions out of their defined position, then what will happen is you'll line up like charges. And we know that like charges repel. So if there's any disturbance of the crystal lattice, you'll end up with like charges next to each other, which will cause the crystal to crack apart. So they're quite hard, but when a force is applied, you get like charges will line up if ions move position, causing cracking. So ionic compounds do not bend, they will just break. Now, in terms of melting point, we think of ionic compounds as having relatively high melting points, certainly higher than regular molecular compounds. So high melting points, much higher than covalent molecular compounds. You can see some examples that I've listed. However, we would consider them to be lower than giant covalent. If you have lots of covalent bonds between all the atoms, like here's silicon dioxide, 1700 degrees Celsius is higher than these other similarly sized compounds that are ionic over here, but still much higher than the molecular compounds that are in the middle. Now, you usually don't have to compare ionic to giant covalent. If anything, you'd be asked to compare ionic to molecular covalent, in which case you would predict that the ionic compounds will have a much higher melting point because ionic bonds are much stronger than intermolecular forces. However, if you look at like comparing different ionic compounds, then the trend is going to be based on similar concepts to the trends for lattice enthalpy, which is that ions that have higher charges tend to lead to ionic compounds with much higher melting points because the higher charges lead to stronger electrostatic attractions. And also, smaller ions are able to pack more closely together and therefore have stronger attractions with their neighboring ions. So, in general, we're going to get higher melting points with higher charges and smaller ions. So those are the exact same factors that affected lattice enthalpy, and that's what will affect the melting point trends of ionic compounds. Let's just slide that up a little bit. Okay, water solubility. Most of the time, ionic compounds are very soluble in water. Not always. There are some that are more or less insoluble. There are some that are slightly soluble. But the reason why they're usually soluble in water is because water is very polar, and if waters come near to ions, the partial charges on the water will line up with the oppositely charged ions, and you'll get what are called ion dipole interactions or attractions. And so a lot of ion dipole interactions can add up to quite a strong attraction and actually overpower the attraction of the ionic bond. And so the ions can be pulled out of the lattice and surrounded by water molecules through these ion dipole interactions. So ionic compounds tend to be quite water soluble, and a key term there is ion dipole attractions. Now, electrical conductivity, you should know that they do not conduct when solid because the ions are in fixed positions, so the ions cannot move. However, if you make an ionic compound into a liquid by melting it, making it molten is the term they'll often use. Then the ions are free to move, and therefore it can conduct electricity. What will actually happen is that the ions will move towards the electrodes of opposite charge and undergo chemical changes, which will keep the electricity flowing at each electrode. But for now, in the bonding topic, you can give fairly simple answers, which is that solid do not conduct because no free moving ions, they have fixed positions, but molten conducts free moving ions. Do not say delocalized electrons or free moving electrons. That is something that they'll be looking for and will never work. Okay, an ionic compound conducts because its ions are free to move. And lastly, ionic compounds will also conduct when they are aqueous, dissolved in water, because once again, the ions are free to move. And that's pretty much it. Those are the properties of ionic compounds that you should know about and that you should be able to explain based on the model of ionic compounds being in a crystal lattice, the attraction between the ions based on how high the charge is and how big they are, ion dipole interactions explaining why they're water soluble, and the moving or lack of moving of ions to explain conductivity.